All right, now we're going to analyze limits analytically, but I'm going to show you a couple techniques that'll make your life a lot easier. Now, this got cut off at the end of the last video. I apologize for that. But this is the dividing out technique. And you've sort of seen me use it without telling you exactly what it is. Now, the dividing out technique is literally redivide the singularity from the denominator out somehow. Basically, you have to do some sort of algebra. So let's factor the numerator, x squared plus x minus 2. Let's see, it needs to multiply to be negative 2 and add to be 1. So I need a negative there and a plus there. All right, and I'm going to get a difference of squares. So this is x minus 1 times x plus 1. And I'm going to leave my limit here. And so I'm going to divide out, change, what's common. So my limit becomes the limit as x goes to 1 of x plus 2 divided by x plus 1. And now, because I no longer have a problem with the denominator being 0 at the point, I can simply plug it in. So this is 3 divided by 2. Or 1.5, I don't care which way you read it. So whenever you have a singularity in the denominator, the first thing you should look to see is if you can somehow divide it out of the numerator. Now, workbook problem, pause, and do this one. Another technique is called the rationalization technique. Now, you'll know your cue to use rationalization whenever you have two radicals that are being added or subtracted. Now you know you can always multiply by 1 over 1. So what I'm going to do is multiply this mess by the square root of 3 plus x plus the square root of 3 divided by the square root of 3 plus x plus the square root of 3. Now this is the limit as x goes to 0 of, let me multiply this out, the square root of x plus 3 times the square root of x plus 3 is just 3 plus x. All right, f, or FOIL, okay, plus the square root of 3 times the square root of 3 plus x minus the square root of 3 square root of 3 plus x minus 3 divided by, this is x times the square root of 3 plus x plus the square root of 3. Now let's go through the numerator and see what simplifies. I know you knew this was going to cancel, but you need to go on and put it in there anyway. This is one of the things I need to see your steps. And let's see, this 3 goes away. Nothing simplifies very nicely in the denominator. Now, do you see how I'm carrying the limit as x goes to 0? See how I'm continuing to write this? I'm left with x in the numerator. X square root of 3 plus x plus the square root of 3. All right, you want to keep carrying this down because this is the problem you're doing. And you don't want to start doing sloppy math and making statements that aren't true. Okay, let's see. Oh goodness, this is going to go away. So now I'm left with the limit as x goes to 0 of 1 divided by the square root of 3 plus x. Be careful with your radicals here that you're being clean, plus the square root of 3. Now we no longer have a problem with the denominator being 0, so I can simply plug in. So this is 1 over the square root of 3 plus the square root of 3, or 1 over 2 square root of 3. Now, on the AP test you won't have to simplify, but in class you will. So get rid of the radical in the denominator. So this is the square root of 3 divided by 6. Was not obvious that was what it was going to be up there, was it? Give it a go. Pause the video, get that one done. Now let's talk about the squeeze theorem. This is also called the sandwich theorem. Suppose I have a function f of x and it's not behaving very nicely for me. It kind of is squiggling around and it's not behaving in a very nice, easy manner for me. What if I knew that the function g was bounded, bounds f on top, and h bounds it on the bottom? And suppose further that I knew that as g went to this value, as g approaches c, g goes to a particular limit, and as h approaches c, it goes to a particular limit. If I can show that f is always between g and h, and the limit of g as x goes to c and the limit of h as x goes to c are the same limit, then clearly the limit of f as f goes to c must equal to that limit as well. It's kind of a sneaky way. You're basically trapping f between f, g, and h. So on these, it's just, you've usually just got to find the one equation, one trick, mind you, that you have to do, or the two functions, h and g, so that f is always bounded by h and g on the upper and lower sides. And you only get these by experience and practicing them. So that's what the squeeze theorem is you're literally squeezing the function between two known functions. All right, let's look at this equation right here. The limit is x goes to 0 of x squared cosine of 1 over x. Now, this can be, how can I put this? A challenge, all right? Because x squared, well, that one's pretty straightforward. But cosine of 1 over x, we've already shown, doesn't work. Well, I know cosine of anything. Cosine of x is always between 1 and negative 1. So negative 1. Come on. It's not wanting to write for me. So I know cosine is bounded. It doesn't converge at that point, but it's still bounded. Now, I know I can multiply through by a positive number, and I'm okay. So if I were to multiply this by x squared, which is positive, it would be negative x squared is less than or equal to x squared cosine x less than or equal to x squared. Did you catch the mistake I just made? I don't really care about cosine of x. I want cosine of 1 over x. So you do this on the AP test. This is exactly what you do. You cross it out. You go, oops, I made a mistake. Negative 1 is less than or equal to cosine of x is less than or equal to 1. Okay, and that's for every value. So it is also true that cosine of 1 over x is bounded by 1. So now I go through and multiply through by x squared. So negative x squared is less than or equal to x squared cosine 1 over x less than or equal to x squared. Now I know the limit as x goes to 0 of negative x squared is 0. And I know the limit as x goes to 0 of x squared is 0. So by the squeeze theorem or the sandwich theorem, therefore, the limit as x goes to 0 of x squared cosine 1 over x is 0. Now, I could multiply through by x squared because it was always positive. Be careful when you're multiplying through by something that might not always be positive. Okay, see if you can do this one. I know it's going to be a challenge, but give it a go. And remember to use that exact same technique. All right, the special trig limits that are really cool. The limit as x goes to 0 of sine x over x is 1. Memorize these. And the limit as x goes to 0 of 1 minus cosine x over x is 0. You can do these given, actually any number of variables. I mean, these are specific ones. But suppose I had the limit as x goes to 0 of sine of 2x over x. What is that? Well, let y equal 2x. And that would mean x is 1/2 y. This is just a trick. So the limit as x goes to 0 is the same as the limit as y goes to 0. And I'm going to plug in sine of y divided by, now x is 1/2 y. Did I do that right or did I do it wrong? Sine 2x. Okay, so that's right. So this becomes 2 times the limit as y goes to 0 of sine of y over y over 2. Now, when you're taking limits involving trig functions, remember to change forms if necessary. Tan is sine over cosine. You may need to change out of secant or cosecant. And then you may need to multiply by a constant. That's what I just showed you. All right, give these a go. Stop the tape. When you're finished, complete your homework.